In this video, we learn how to predict the shift in an equilibrium when we change the conditions under which the equilibrium is by stating the Chatelier's principle. Right, so the idea is that we're going to have a system at equilibrium, and then we're going to modify that equilibrium by doing something. Maybe we're adding more of a reagent, or we're adding more of a product, or we're removing a product, or maybe we're changing the pressure, or we're changing the temperature. There's many ways that you can affect a change in an equilibrium. The question is whether we can predict what is the direction in which the equilibrium will shift when you do that modification. Well, it turns out that there's a very simple way to predict the way in which the equilibrium will shift, and that is what we call the Chatelier's principle. So the principle states that when you disturb an equilibrium, then the equilibrium will shift to minimize the effect of the disturbance. Right? So it's a very simple statement, and we're going to see how that plays out using a couple of examples here. The first one is going to be a reaction in solution. So we're going to have a generic A plus B to give C plus D reaction with 4 solutes. And the reaction is going to be at equilibrium to start with. And let's assume that the concentrations of each one of the species at equilibrium are 0.1, 0.2, 0.3, and 0.4 molar. Okay, so this is already at equilibrium. And then, of course, the first thing that we can do is calculate what the equilibrium constant will be for this, right? So, because those are the concentrations at equilibrium. And the equilibrium constant in short form is simply the concentration of D at equilibrium times the concentration of C at equilibrium over the concentration of A at equilibrium and the concentration of B at equilibrium. Then you can punch in the numbers there and find out that this equilibrium constant has a value of 6. Okay, so that will be your equilibrium constant. Again, the system is at equilibrium. Now we're going to modify this, right? So what we're actually going to do is just dump more D into the reaction mixture, right? So suppose that D is an ion or a salt, and or a sugar, any molecule, and then we can sprinkle a little bit of it on the reaction mixture so that the concentration increases to 1.0 molar. At that point, we're no longer at equilibrium, and then the system will shift to re-establish equilibrium. That's how equilibrium works. Okay, so the idea is, well, can we actually use the Chatelier principle to predict what is the direction of change of that equilibrium? Right, so the disturbance has been to add more product, right? And Le Chatelier's principle says that, well, the equilibrium will shift, the reaction will shift to minimize that disturbance, right? So if the disturbance is to add product, a way to minimize that disturbance is to actually make the reaction or shift the reaction towards reagents so that that excess product that you have added gets kind of back reacted into reagents, and that minimizes the amount of D that you have added. Okay, so that will be the prediction of Le Chatelier's principle. The equilibrium in the system will shift from right to left so that we drop the amount of D that we have added, okay, which happens to be 1.0 molar. Okay, so that will be the prediction, and then we can actually go and carry out the calculation and see if our equilibrium calculations bear out Le Chatelier's principle's prediction. Right, so now my initial concentrations will be 0.1 molar. There's nothing that I have done to A or to B or to C. The only thing that I have done is just change the amount of D. Okay, so then we can predict here the change. We're estimating that the reaction is going to shift from right to left, products to reagent. So what that means is that there should be a growth in the amount of reagents, and then products should decrease. Okay, so then the concentrations at equilibrium will be 0.1 plus X, 0.2 plus X, 0.3 minus X, and then 1.0 minus X. Alright, so then we can go on and try to calculate that equilibrium constant. This is going to be equal to 1.0 minus X, and then multiply by 0.3 minus X, and then multiply by the concentrations of reagents, 0.2 plus X, and then 0.1 plus X. Okay. And when you do that, then you find, and this has to be equal to 6. Okay, so then when you do that, you find that x is equal to 0.053, assuming that we have two significant figures in all of the concentrations. All right, and then what that means is that once you get back to the equilibrium row here, this final concentration is going to be 0.15 molar, and then 0.25 molar. Let me erase this. This is going to be 0.25 molar, and that will be 0.95 molar. So clearly, the equilibrium calculations have borne out the prediction by Le Chatelier principle. Okay, the idea here is that we have moved from a situation where we had too much D. Okay, we had an equilibrium, we have added D, so there was excess D. Now that D has, the reaction has shifted to reduce that amount of D and then regain equilibrium, right? So these are the new equilibrium concentrations that demonstrate that yes, the system has shifted from right to left. Okay, so that is kind of a first demonstration of the validity and the usefulness of Le Chatelier's principle. We're going to do a second example that is going to show how this applies to a gas-phase reaction in the next video.